Hi everybody, I'm Radek Zagórowicz from Epsilon team on Ethereum, and today I'm going to talk about EVMMAX, which is the extension we are planning to add to the EVM. So the talk consists of three different parts. In fact, first I will try to introduce you, but I think for most of you here, it's not very needed to the precompiles, what they are, and what problems actually we have with them. Second part will be just the introduction to the EVMMAX and some technical details I would like to talk about. And the last thing is I would like to describe you some prototypes and examples we prepared already based on EVMMAX prototype. So the compilers, the precompiled contracts, probably as I said, probably most of you already know what it is, but there are a couple of facts they are worth reminding here. So a precompile is an account which basically works as a contract, but it doesn't have a bytecode. The way it works is defined in the specification, not as a bytecode, not as a EVM instructions, and they are implemented basically in the execution layer clients according to the specification. And there is a special address pool which is reserved only for the precompiles, and now we have, I believe, 10 active precompiles actively available from the EVM, and they are just addressed from 1 to 10. And because they are from the EVM perspective as a regular contract, they need to be called as a regular contract, and they return the results on the stack on the EVM stack. So this is the list of the currently available precompiles, and as you know, as you can see, most of them are somehow related to the elliptic curve, to the cryptography in general, and to elliptic curve cryptography. So basically, the purpose of having precompiles in the EVM is to have advanced cryptography available in the EVM. But basically, precompiles are controversial, and I would like to list a couple of points which makes them controversial. So, at first, we always have a discussion what should be added, and there are a group of interest who pushes some changes which will be beneficial or useful for their projects because they can do something easier, cheaper, or something like that. Moreover, there is always a temptation to move some functionality to precompiles because it's hard to implement it. It's in the pure EVM, and it's also really hard actually to add different precompiles. Sometimes it takes years, and people are promised that some functionality will be added, and it takes, for example, 3 years to be finally introduced. And very often after this time, it's this functionality is already useless. Like in example with a couple of different precompiles. So, and what's other thing is which is worrying regarding the precompiles, that there is a long list of proposed precompiles which people or the community would like to add to the EVM, and it means that there is a strong need from the community to have such a functionality, but the only way we can have it now is just to add them at the precompiles. And so as you can see, maybe I will, but it's difficult to add it, and sometimes it takes years to do it. And there is a very important thing regarding the risk of the consensus itself, because how it's implemented now put the consensus on risk. And we have a couple of examples already mentioned by, for example, Mariusz from Gov team regarding XMod, and a couple of different things. So, and we believe that that's enough reasons that we need better solution, and that's why we started working on the EVMMAX. So EVMMAX is the EVM modular arithmetic extension. So what was the motivation for the EVMMAX? One part is the general problem with the precompiles, but another part is to make future development of ECC related functionality much easier and independent from the Ethereum protocol development. We define a list of most important motivations for introducing EVMMAX. So at first, EVMMAX allows us, as I mentioned, to implement ECC arithmetic operation as a EVM contracts. So everybody of you can have its own ECC implementation and use it without any risk for consensus and security of the protocol itself. And we can also potentially consider implementing a standard ECC library available as a set of the cryptographically specialized contracts and the libraries in Solidity or Viper. Secondly, because of the better optimized implementation, we can significantly reduce the gas cost of the operation on 256-bit values, which is used to, for example, if we want to, for example, we will not have to push all the parameters, for example, needed by the addmod and mulmod on the stack, and then the instructions will have to get it on the stack and based on this make the computation. But for example, add and mut, anytime we call it, we need to pass the argument with the modulus. And if we implement some more advanced functionality using these two opcodes, anytime we have to pass exactly the same modulus as an argument to this opcodes. So sorry. Yeah, but there's this advanced algorithm, basically modulus in most of the cases is constant, so we don't need to push it every time. Moreover, in this model, XMod, so already mentioned, precompile, can be implemented as a EVM contract. Now it's difficult to do it because mulmod opcode, which is used to implement XMod, is too expensive in gas and it consumes 3 different parameters, as I mentioned, instead of at least 2. And as you see later in EVMMAX, it will be more optimized. Yeah, and the last but not least, it will allow us to reduce the gas cost of the cryptographic hash function calculation and also ZK proof verification. And the reason is exactly the same, that we have much faster and much cheaper in gas operation like addmod and mulmod. Yeah, so also in EVMMAX we'll be able to implement algorithms which based on different modulus sizes, not only 256, but also for like for BLS curve, we have a modulus which is 381 bits, and now it's really difficult to implement this in the EVM, but with EVMMAX it will be supported natively. So to have EVMMAX working, we need to introduce a couple of new opcodes. So first one is the setup X, and this instruction together with passed parameters creates a new active modulus if it doesn't exist yet. Every modulus context is fixed; it cannot be changed after the creation. On modulus initialization, it calculates also some specific parameters or constant which will not be changed during the computation, like for example R² parameters on R prime parameters, use it to make a computation in the Montgomery form, which is useful to optimize cryptographic algorithms. And of course, if the modulus doesn't exist, it's created, as I mentioned, and it supports different sizes of the modulus, so this different sizes of the values, etc. Setup also defines how many slots. We can think about slots like processor registers are available in the context we will be implementing, or actually the implemented algorithm will be computed. So another two instructions are store X and load X, and basically these instructions are responsible for transferring values between EVM stack and EVMMAX memory slots. What's important is that the fact that loadx and storedx values are converted to and from Montgomery for automatically when they are transferring between these two contexts. Yeah, so basically it's worth mentioning also that it's transparent from the context of the EVM. And the last three instructions are typical modular operation instructions, which probably I don't have to describe here, and I'm not going to do it. But it's worth noting that they are taking their parameters from the EVMMAX memory, not from the EVM memory, and they are returning results also to the EVMMAX memory. They require immediate opcodes, parameters, which will be introduced together with EOF. And we don't have, was also worth noting that we don't have to, anytime we need some calculation like add mod or mul mod in the EVMMAX, we don't have to transfer values between these two contexts of EVM and EVMMAX, because most of the computation are done inside the EVMMAX context, and in the end, after some very long function, we can only, if we need, we don't have to, if we can read the values computed in the EVMMAX context loaded back to the EVM stack. So to summarize, we have three different types of instructions. One is setup X. Second type is loadx and storex, which are responsible for transferring values between EVMMAX and EVM stack. And the last one are just three very simple modular arithmetic instructions. And here we can see how potentially we'll look the comparison between the legacy or actual EVM and calculating the add mod, and calculating exactly the same using the EVMMAX add mod X instruction. There are a couple of reasons why we think that the cost of the ADMOX X can be much lower than the cost of regular ADMOD, which is now available. So the couple of them there, but I'm going to list only three, the most important. So the first, that we don't need input verification. So we are already sure that these values A and B are from the proper field of modulus. So they are not bigger, for example, than modulus. The modulus is odd already, and so we will not have this weird cases where someone calculates modulus calculates ADMOD with even modulus. And as I mentioned, they will be already in Montgomery form, so we can use much more effective algorithms. So, and there are some examples and prototypes we implemented, the list of it. So, basically we implemented C++ API to EVM, which implement the EVMMAX API. And using this API, we implemented a couple of precompiled functionality counterparts in the EVMMAX. So as you can see, it's like EC recovery, which is used to verify Ethereum signature, point addition and doubling for beyond the 254 curve, point multiplication, EC pairing also, which doesn't have a PR yet, but it's already in our branch. And we started also implementing some functionalities from the BLS curve, which so now we implemented EC add, but the rest is in progress. And we plan to implement KZG and point evaluation precompiles in the near future. So how we did it? Basically, we use some well-known tools to implement the modular inversion. We use add chain generator, also the same for square root. For point addition and double, we use some well-known formulas from Castello-Bettina paper. You can find the link below. And for point multiplication, you use just regular Montgomery ladder algorithm, which uses point adding and doubling from the point above, which point adding and doubling formulas from the point above. So what's the conclusion? Conclusion of this work is that we are not basically cryptography experts, but it appeared that it's kind of easy to implement precompiles functionality in EVM using EVMMAX. And probably there are a lot of people here who will implement it much better than we do. But the best of it is that you can start, assuming that we have EVMMAX delivered, you can start implementing your ECC cryptography using EVMMAX in EVM without a risk for a consensus or waiting for needed precompile to be delivered by the protocol. So here you can find a link to our EVMMAX branch in the EVM1 project. Secondly, here is the link to the, I think, latest EIP now for the EVMMAX. And in the end I would like to present you a list of persons who are involved, or were involved in the project, and we are developing it. So basically, mostly Epsilon plus Jared, also from VF. Many thanks to him. Yeah, that was that. Thank you very much for your attention. Hopefully, it was interesting. Thanks.